I'm Sanika Ijantakar of CS department from KLEIT Institute of Technology. I'm presenting my project on skin cancer detection and using deep learning. Before moving on to explore the code, I would like to briefly explain the importance of skin cancer detection. We know that skin cancer is one of the most common cancer worldwide, and the early prediction can help to increase the survival rates. But the manual diagnosis is time consuming, and which is why we are using deep learning to enhance the speed of diagnosing the disease. So with this understanding, let's explore the code. First, we set up our environment by mounting the Google Drive to save and load files using from google.colab import drive.mount, and the path is specified. As we can see here, that drive is already mounted at the particular path, and then we install the necessary libraries, which are TensorFlow, Keras, NumPy, Pandas, and Matplotlib. Then we will also install Keras Tuner to balance the data set. Here we are installing the Kaggle. We are importing Kaggle library to our Colab Python using pip install Kaggle, and then we are making a Kaggle directory here using mkdir.kaggle, and then we are copying the uploaded Kaggle to this Kaggle directory. Then this provides us rights to for our Colab. And then we are also importing some of the necessary libraries for the following purposes. We are importing OS to interact with the operating system. Then we are importing CB2 for image processing task, as our model takes the image from the user as input and then processes the images, and then the final result gives the final result. Then we are importing NumPy as NP for numerical computations in Python. Then we are using TensorFlow. TensorFlow is an open source free library for machine learning and deep learning, which is used for CNN. Then we are using sklearn to create neural network models. Here we can see that we are using we are downloading the data set for our model from Kaggle using Kaggle dataset download, and the path is specified there. Then we are extracting the contents of the zip file using unzipped skin cancer dataset. This is the path here. And we can see that the contents are being extracted. In our dataset, there are two types of cases. First is benign, and another one is malignant. And we can see here all the cases have been extracted. Then here we are defining the directories. First, we are specifying the main directory in the variable train dir. Then we are defining the path for benign skin cancer images, and similarly we are using the variable malignant dir for defining the path for malignant skin cancer images. Then we are importing the necessary libraries of TensorFlow.keras for processing the images. We are setting up data augmentation and pre-processing in the variable train data gen using the function image data generator. Then we are creating batches of augmented images in the variable train generator using the function train.data.flow from directory. Here, and the parameter specified here is train dir, and the target size is of 150 by 150, and the batch size is of 32, and the class mode is binary. We can see that here we have found 270 images belonging to two classes. As I said earlier, the two classes are benign and malignant. Then we are specifying our model, which is CNN model, using the Keras tuner. Here we can see that we are specifying declaring the class CNN hypermodel. In that we are defining a function build, and the parameters are self and HP respectively. Then we are creating a sequential model in the variable model, and the following code, the below codes, adds layers to the CNN. This code adds convolutional layer with adjustable filters, and this layer adds the map pooling layers to downsample the feature maps. And this last code flattens the 2D into 1D vector. Then we are compiling our model, and then the model is being returned here. This creates the model with tunable parameters. Then in the variable HP, we are creating a hyperparameter object. Using the hyperparameter object, we are building the model. Then finally, we are building the model summary. We can see that there are some following layers in our model. The first one is Convo 2D layer. The second one is Max Pooling 2D layer. Then Convo 2D layer. max pooling layer, flattened layer, dense layer, and again dense underscore one layer. And the output shapes have been given here with the parameters respectively. Then from the TensorFlow library, we are importing Atom, and in the while compiling the model, the optimizer is Atom with the learning rate of 0.001. Then here we are setting up the Keras tuner in the variable tuner with the function random search, and the maximum trials we are giving is 10 to increase the accuracy of our model, and the executions per trial is 1. And then we are setting the hyperparameter search here. Then we'll get the best model after the search in this variable best model. Then we'll evaluate our model. We can see that the accuracy obtained is 96.67%, which is quite good accuracy for a basic model. We can also improve the accuracy of the model in future by changing some of the functions. Then we are importing scalar matrix, importing confusion matrix from the library scalar matrix. Then we are predicting using the best model. In this variable prediction, we are predicting the model. Then we get the true labels. Then we generate the confusion matrix, and then here we plot the confusion matrix. Confusion matrix shows the classification performance of a classification table. We can see that this is our confusion matrix, and the true label is malignant and benign, and here we get the predictable level. Here we are saving our model. Here we are saving the model, and we have specified the path which will be saved in our Google Drive, and we can access it whenever we want. Then we are loading our model, loading the trained model, and we are defining the function preprocessed image. Here we are loading our image. The path is specified here. Then we convert the image to RGB. RGB is a color mode. If it is not in that form, it will convert to RGB mode. Then we are resizing the image to the target size, which is a 150 by 150. Then we will convert the image to NumPy array form. Then we will normalize the image. Then we expand dimensions to match the model input. And this function definition predict image, we are predicting the image on the basis on the two classes, either malignant or benign. Then we process our image. Then we give the result here. We will also display the image given in the path using matplot library. We are also defining the we are giving the image with the predicted class. We can see that I have given the image path of malignant skin cancer type, and we got the output as malignant, which is 2. And this is the image which I have given as path. After this, we are deploying our code in Streamlit library. To install Streamlit library, we have to use the code pip install -q Streamlit. Then we are creating a Streamlit app for skin cancer detection. Again, we are loading the model by specifying the path. Then we are pre-processing our image in the function. Then we are predicting our image. UI allows users to upload image and view predictions. Here we are uploading the image, and we get the our output. Whether what is the class of the image. Then we'll install local tunnel to expose the Streamlit app to the web. Then we'll run the Streamlit app and display the public URL. You can see that we got the URL here, and this is the password for tunnel. Here we will paste the password, and we will get the interface for our application. Now we will upload an image. I am uploading an image of malignant. Let's see whether our model predicts it correctly or not. It's getting loaded. This is the image I uploaded, and we got the prediction as malignant, which is true. Now let's check for another case. I have uploaded the image of a benign skin cancer type, and as we can see that the prediction is correct. It has given it as benign. The application of this model is that it is user friendly. User can easily upload the image and get the predicted skin cancer type, and it helps in early detection and diagnosis of